Welcome dear students to lecture 3 of module 3 time response of feedback control systems. In today's lecture, let us learn about steady state errors and the error constants. Steady state error and error constant. A steady state error is defined as the difference between reference input and the final steady state output. It is measured with respect to different standard test signals. They are step input, unit ramp and the unit parabolic signals. Now let us consider a unity feedback or a non-unity feedback system over here, okay, where g of s is the forward path function and h of s is a feedback path function. Now let us find what is the steady state error in this case. Now here, see e of s, here we have the error, right, e of s. Now what is e of s? E of s, according to this, will be see summation point we have. So one input of the summation point is r of s. Other input is h of s. But where is h of s signal coming from? C of s. Alright. So we have h of s into c of s. Let me take this r of s out. So what do we get? 1 minus c of s by r of s into h of s. But what is c of s by r of s? We already know, right? For a for feedback system, negative feedback system, what is c of s by r of s? We know it as g of s divided by 1 plus g of s h of s. So let us substitute it over here. So r of s into 1 minus g of s divided by 1 plus g of s h of s into what, this h of s which is already there. So if I take this r of s and if I take common denominator 1 plus g of s h of s, here in the numerator 1 plus g of s h of s and here minus g of s h of s. Okay, so this you can cancel out. Here what will remain? R of s by 1 plus 1 by r of s by 1 plus g of s h of s will remain. So here e of s. Okay, so e of s will be r of s divided by 1 plus g of s h of s. Now what is steady state error by definition? It is the derivation of the control output from the reference, deviation of the control output from the reference input. If E of t is error in time domain, E of t is in time domain, okay, then E of s is the Laplace transform of this. Then steady state error ESS, this is a steady state error that can be expressed as limit t tends to infinity E of t by using final value theorem. We can write this as ESS is equal to limit s tends to 0 s into E of s. So if I substitute here limit s tends to 0 s into r of s divided by 1 plus g of s h of s. This is the steady state error. Now let us apply these for different inputs and see what are the steady state errors we get due to different inputs. So previously we have generalized form we have seen for the steady state error. Now let us consider the unit step input. So how do we represent a unit step input? That is R of S is given as 1 by S. What is the steady state error given by ESS? Generalized form first I read. ESS is limit S tends to 0 S into R of S divided by 1 plus G of S H of S. Now let us substitute for the input. We know it is step input, right? Unit step input we have considered. S into 1 by S divided by 1 plus G of S H of S. S and S I can cancel out, right? Now when I cancel out S and S, what we get? We get limit S tends to 0 1 by 1 plus G of S H of S, right? See, 1 and 1 I cannot apply limits. Where can I apply limits? I can apply limits for only here, right? I can apply limits for 1 by 1 plus G of S H of S is a function of S, right? So I can apply limits to that. 0 G of S H of S. This is the steady state error over here. So what we'll do, we will consider that ESS, I will write it as 1 by 1 plus KP, where KP is equal to limit S tends to 0 G of S into H of S. Okay, where what is KP? KP is known as the positional error constant. So if we have step input, then the error constant is known as the positional error constant. What is a steady state error? Steady state error ESS is given by 1 by 1 plus KP. Okay, next let us consider the ramp input. Unit ramp input. How is unit ramp input represented? The Laplace transform R of S is given by 1 by S square, or if you want it in time domain, how is it? R of t is equal to t into u of t, where u of t is a unit step signal. Now the steady state error ESS, it is given by limit S tends to 0 S into R of S divided by 1 plus G of S H of S. So here I can write it as limit S tends to 0 S into R of S is 1 by S square divided by 1 plus G of S H of S. So 1 S will get cancelled here. So limit S tends to 0. I get 1 divided by S plus S into G of S H of S. So when we apply the limits, this will become 0. So what will remain? I can write it as 1 divided by limit S tends to 0 S into G of S into H of S. So I can write this as 1 by KV. So ESS is 1 by KV, where what is KV equal to? KV is equal to limit S tends to 0 S into G of S into H of S. This is the, now what is this KV? KV is called the velocity error constant. and the steady state error due to the ramp input is given by 1 by k t. Okay, so we are done with two inputs, step input and the ramp input. Next is the parabolic input. So let us consider the unit parabolic input. So how do you represent a parabolic input? R of t is given by t square by 2. If I take the Laplace, R of s is given by 1 by s cube. So let us write the steady state error. ESS is equal to limit s tends to 0 s into R of s divided by 1 plus g of s into h of s. This is equal to limit s tends to 0 s into 1 by s cube whole divided by 1 plus g of s h of s. So here square will remain, right? So this will be limit s tends to 0 1 by s square plus s square g of s h of s. When I apply limits, this will become 0 s square term. So what will remain? So ESS will be, I can apply limits to 1 by limit s tends to 0 s square g of s h of s. So here I can write this as 1 by k a we will write. So this is a steady state. What is ka? Ka is given as limit s tends to 0 s square into g of s into h of s. This is the acceleration error constant. So Ka is called the acceleration error constant. So the error constant due to the parabolic input is called the acceleration error constant. Okay, and the steady state error is given by 1 by Ka. Now we will see what is meant by type of the system. See, open loop transfer function of a unity feedback system can be represented in two standard forms, the time constant form and the pole zero form. So first we will see the time constant form. So a g of s can be written as k into t z1 s plus 1 into t z2 s plus 1 so on, okay, divided by s to the power n t p1 s plus 1 into t p2 s plus 1 and so on. Okay, this is called the time constant form. Then one more form is the pole zero form. So that I can write k dash s plus z1 into s plus z2 so on divided by s to the power n s plus p1 into s plus p2 so on. This is called the pole zero form. Okay, here see we have the term s to the power n, this term and this term. Here we have n, that n is called the type of the system. Or what is a type? Type is the number of poles at the origin. That is called the type of the system. This you have to remember. And this is for an open loop transfer function. Whereas order is for the closed loop transfer function. It is the number of poles in the transfer function. Okay. Number of poles of the closed loop system. That is order. Type is the number of poles at the origin. Now here we will see the error constants for different types of system. So first we'll consider for type 0 system. Means what is the meaning of type 0 system? There is no pole at the origin. Okay. So how do we represent such a system? So in general I can consider the open loop transfer function as some constant k and a numerator and a denominator which is a function of s. It is in Laplace transform. Okay. We don't have any pole at the origin. Means it is s to the power 0. Alright. So I don't have to write over here. So first we will find the positional error constant. So positional error constant. So what is positional error constant? Kp is equal to limit. We already derived, no? Limit s tends to 0, g of s into h of s. H of s, if it is a unity feedback, it is going to be 1 over here. Okay. So let us consider it is an unity feedback. So I'll write it as 1 over here. So limit s tends to 0. Okay. Or it is written together. G of s into h of s is k numerator and this. Alright. So s tends to 0. And what is g of s, h of s? It is the transfer function. Let us write d of s. Now, when I apply limits here, what happens? We get a finite value. We don't know what is the value. We get it like this. Some limit we apply. So this is a finite value over here. Okay. So Kp we get it as some finite value. Some, say I'll consider this as some K dash. So what happens to the steady state error? ESS. ESS is given by 1 by 1 plus Kp. So I can write it as 1 by 1 plus some K dash. So we get a finite steady state error for a step input. Okay. What is the meaning of that? That is, if it is, this is a step input, some steady state error is there. This is the steady state error. Some finite error we get over here. Okay. Next, if we consider the next case, that is the velocity error constant for a type 0 system itself. So we know, I'll write g of s, h of s. So I'll write it together, considering it as k into numerator and denominator over here. Okay. So what is kv? Kv is given by limit s tends to 0, s into g of s into h of s, which I substitute here, 0, s into the transfer function. Okay, see here we have in s into something. When I apply limits, what happens to this? Whole thing becomes 0 over here, right? Because this term does not cancel. Apply limit, it will become 0. So what happens to the steady state error ESS? So ESS will be 1 by kV. So it will be 1 by 0. We get an infinite steady state error for a ramp input. If you apply ramp input for a type 0 system, we are going to get an infinite error. Next is the acceleration error constant. So here Ka is equal to limit s tends to 0, s square, g of s, h of s. So limit s tends to 0, s square into, we know that, right? K into numerator and a denominator. Here also, what have s square into something? So here also I'll get it as 0 only. K A. So what happens to the steady state error? 1 by Ka. So this also is 1 by 0. We get the, again the steady state error here also as infinity. So for a type 0 system, we get a finite error for a step input and infinite error for both ramp and the parabolic input. So previously we have seen the error constant for type 0 system. Now let us consider type 1 system. So what are the error constants? We get for type 1 system. Okay. So how do we represent a type 1 system? So G of S is H of S, K, some numerator, and in denominator we have S. This is type 1. So S to the power 1 here it is. Therefore it is type 1 system. Okay. So now, first one, what is the first thing? Positional error constant. Okay. Positional error constant. So Kp is equal to limit S tends to 0 G of S into H of S. Limit S tends to 0 G of S, that is K numerator S dash or S to the power 1, it is not dash, S to the power 1 or S, right, over here. So what happens over here when we apply limits? We get this as infinity because this will be by S, no, 0. By 0 means what? It is going to be infinity. So what happens to the steady state error ESS? It is 1 by 1 plus Kp. So 1 by 1 plus infinity. What happens to 1 by 1 plus infinity? We get the answer as 0. So if we apply a step input to a type 1 system, the steady state error is going to be 0. That is, the output follows the input. Exactly this, without any error. Next is the velocity error constant. So here Kv is equal to limit S tends to 0 S into G of S into H of S. So limit S tends to 0 S into the transfer function type 1. So we have S in the denominator. S and S gets cancelled. So what happens? When I apply limits, some finite error constant, I'll get some K dash, let me consider it as. So what do we have? Kv is K dash. What is the steady state error? 1 by Kv. It is 1 by K dash. Some finite error we get over here. So if I apply a ramp input to a type 1 system, we are going to get a finite steady state error. And the last one, let us see the acceleration error constant. So here Ka is equal to limit S tends to 0 S square into G of S into H of S is equal to limit S tends to 0 S square into K, the transfer function S into D of S. So 1 S will get cancelled. So S into something, when we apply limits, we get it as 0. So what happens to the steady state error? It is 1 by Ka or 1 by 0. So what do we get? We get an infinite steady state error. So for a type 1 system, if we apply a step input, you are going to get a 0 steady state error. If you apply a ramp input, you are going to get a finite error. And if you apply a parabolic input, you are going to get an infinite error. So last thing over here, let us find the error constant for type 2 and higher order system. type 2 and higher order system. So here, how do we represent type 2 system? So let me consider g of s, h of s is equal to the numerator. In the denominator, what do you have? Type 2 means you have two poles at the origin. So it will be s square and the denominator. So first one is the positional error constant. So we have here Kp is equal to limit s tends to 0 g of s h of s is equal to limit s tends to 0 k, the transfer function, s square and the denominator. So what happens when you apply limits? You get it as infinity. Something by s means s is 0, you get infinity. So what is the steady state error? ESS is equal to 1 by 1 plus kp. So that is 1 by 1 plus infinity. You get it as 0 steady state error. Next, let us consider the velocity error constant. So velocity error constant kv is equal to limit s tends to 0 s into g of s into h of s. So here limit s tends to 0 s into the transfer function s square, type 2 system it is. So 1 s will get cancelled, but still we have s in the denominator. So again we are going to get the velocity error constant as infinity. What about the steady state error? 1 by kv, which is 1 by infinity, which will be equal to 0 over here. So next, the last one is the acceleration error constant. So k a is equal to limit s tends to 0 s square into g of s into h of s. So here I apply the limits. Limit s tends to 0 s square into the transfer function s square and denominator. S square and s square gets cancelled. So what do we get? We get a finite error constant. Let me consider it as k dash. So what is the steady state error? 1 by Ka, which is 1 by K dash. Some finite error we are getting. Okay. So if I summarize this type 2 system, if we apply a step input to a type 2 system, we are going to get a 0 steady state error. If we apply a ramp input to a type 2 system, we are going to get a 0 steady state error. But if we apply a parabolic input, we are going to get a finite error, steady state error. So this is about the steady state error and the error constants.